Okay, we're looking at decision trees in UML. We're reading this code. This is some Python code from a guy at Google that makes YouTube videos about machine learning. And this is his implementation in Python of a decision tree. And so we're just reading this code and we're translating it into UML. And then we just want to come up with basically like a UML implementation of a decision tree, which I guess should be really called more of a specification. But I'm going to call it like an implementation to get the point across that it's like a complete specification that's almost executable, like if you could execute it by hand or something. Now, I don't know that we're going to reach that goal, but that's just that's kind of the idea in any case. And already, did a session yesterday, and then when I was done, realized I definitely am doing some things wrong. But that's okay because I'm really I've used UML a bit, but I'm not an expert at UML. I'm not sure there's many of those guys around, and it's certainly not to do like what I'm trying to do. So I've made some mistakes. But the first big mistake I saw was that I called this thing a feature, and the first time I talked about it, I said instance. And that was the correct thing because a feature, if we look at some training data, I don't know where the training data is in this source code. So if we look at some training data, each array, or really we should call them a vector, or it's Python, so we should call it a list. But in each of these Python lists, each element is a feature, right? So the first feature will be whatever color, the second feature will be whatever that is, the size, and the machine learning thing, we don't care what these things represent. We just, as long as they all are the same, so all 3, 3, 1, well, that could be the number that we have or the size of it, or doesn't matter, the number of leaves that it has on it. It's not important. And then this last thing is the prediction, actually, like what we would classify it as. So these first two columns are the features. So I don't give a feature in this use case or this sequence diagram. I'm not saying here's an example, aka a feature. I'm saying here's an example. And so let's just go ahead and call that an instance. So I'm just going to fix that right away while I'm here doing it. Let's just do it. All right. I'm going to open it up fresh here. And that was the use case. No, that was the sequence diagram number 1. So the other thing this brings up for me is that I would like to use UML, and I guess maybe this is where we could use like the class diagrams or something, to sort of say what things are. So, for example, like, I guess the class diagram is where you can describe the components of a system. But like, so I need to have a class for like an instance. Like, what is an instance? An instance has features. And like, for instance here, where is it? So when we're talking about finding the best split, and we're saying we have gain and question, okay, well, how do I define what gain and question are? Well, I think for that, actually, everything needs to be some kind of class. So yes, in Python, gain and question are not classes. I mean, technically, like everything in Python is an object. So gain and question are, some instance of like a integer object, or it's a dictionary object, or whatever it is. But we want to conceptually represent what is everything that we're talking about here. So how do we explain in UML what is gain, what is question, and let's get all of our terminology right, And also question, I think I'm going to call that test instead. For my purposes, I'd rather call it test than question. I'm not sure. You could call it question, I guess is fine, but we want all of our, especially since in UML it's really more of a specification, but I think even just in regular code, we want to name everything so that it's very obvious exactly what it is. Now, question or test, either one of those names, it's not super obvious. So if we can name this in a way, at least in the specification, at least in the UML, in a way that's more obvious what we're trying to do, that's better. So that's a couple of things that I learned from doing this last time. So now if we, let's see, we can maybe rebuild these guys. Did that work? I'm not sure that did anything. No. Okay, let's, source RC. Let's make sure we can build our images. Yeah, that it did build it. Okay, and here we say, here's an instance. Okay, so that's working. And again, we started out just with some notes here. It's really just like, this is just scratch. This was just me taking things that I saw in the code, and that's like, okay, we have a thing that's going to, get true or false rows and get the info gain. And we don't really know where these things belong, but we just wanted to write it down. But we know that we have a decision tree, can either build a tree or classify. These things are pretty solid, but very simple. And then we got down to looking at this building of the tree. And I created a state diagram. And so another thing I learned is I look at this and I wonder, is a state diagram really the correct because I'm talking about state, but I'm also I am kind of showing the control flow here, right? The state basically is that you're building more of the tree or you're returning a leaf of the tree. This is actually more like an activity diagram. So that's probably what I should have used in the first place. I got confused because I was wondering, this state of info gain, right? But this is probably like a bastardized state diagram. It's really an activity diagram, but I just use the state diagram things to draw it. So I'm pretty sure I screwed this up, which is fine because I'm learning all this. But let's try to do it as an activity diagram and see what comes up that's different. And I'm pretty sure that as I keep doing this, I'm going to get faster and faster at understanding how to represent all the code as diagrams. So we're just basically looking for what does a loop look like? Yes. So, and this is it. So we could basically have done, and this is even better because now I can actually even label. I mean, I can almost just copy this and this becomes it. Okay, so I was worried also about having to label the decision node. Like here we have a decision node. That's what that diamond means, I guess. Where is it in here? I think it's just, yeah, it's just unlabeled. I don't know. I will, whatever. let's just keep moving forward. Okay, so activity 1, and I can actually just put this in here. Wait, what? I may have a slight problem here. Did I never create a state thing? Okay, so my state diagram actually is still saved in here as activity 1. So what it should have been, call this state 1. Wait. Hold up. Let's just save this as state 1.plant UML. So that's cool. And now we can open activity 1 and we can overwrite what's in here. Like so. And so we can render everything. So now we're going to lose this state diagram because it's now called state 1. And here's activity 1. All right. Okay. So that's something. And now we're going to make it look like our function. Okay, so more data, right, is basically gain of info. So while there's a gain of info, it's going to be like we're going to split it into the true branch and false branch. Something like that. It's not going to be totally precise, but yeah, because we actually kind of want this to split here. You know what I mean? And we'll see. I'm sure I can probably split this. So foo as starting label. Sure. I'm just going to be build a branch of decision tree. So I want something here before the stop as well, which is basically going to be the return a leaf. But anyway, let's forget it. Okay, so here we're going to get. So we need to. So we're going to call it test for now, but I want some terminology that's better than test. So we're going to say find, let's call it a feature test or something. That returns the highest gain of information. I'm not sure that this is like totally correct, but at least we're getting closer. So we're going to build a branch of the decision tree. We're going to find a feature test which returns the highest gain of info. Is there a gain of info? They're going to create the true and false branch. And let us see if we can now split that up maybe. Let's just kind of scan through this diagram for like a. So this one seems to split. Okay. So they had something went wrong. Where's that? So repeat while something wrong is yes, not no. Okay. So no. I'm not really into how they have this like pseudo code you have to write, but whatever. It's going to be okay. So here's okay. So something went wrong. Then if something went wrong, then no. So here's an if. Right. Let's just go to a simple conditional switch. I don't know. It's not really like a condition. It's literally like I'm starting 2 new processes. You know, so I just want this one action to like lead to 2 new actions. Parallel processing. There it is. Perfect. Perfecto. That's what we're doing. Or split processing. That's even better. Because we don't really care that this is parallel or whatever. So this is the input split. This is you can just split. Wait, what is split A, split again B? Let's try that. Let's see if we can make this work. Okay. So this is backwards. How do I do the backward and the split together? I don't really know about this. How do we do backwards? Let's find backward first. All right, so it says this one just has this example. This is backward. Okay. That's another backward. It's fine. Okay, nothing crazy going on here with the backward. I mean, nobody said I was going to like really quickly figure out how to make a recursive function clear in UML. I want to do split, end split. However that's supposed to look. Split, so we have a split and then end split. It does not have a semicolon. Okay. And then we have split, and we have our thing, and then we have split again. So our thing, now the use of this backwards, we're going to have to figure out where that's supposed to go exactly. But we have split and then split again and then end split. And are they all going to be backwards? This backward thing might totally screw us up, but that's fine. So how do you do it? It's like that, just like that. And then you say, can you come back here? Why does these things always need to indent so crazy? Split again. I don't know if this is going to work at all. But error in line 9. Yeah, the backward thing just wasn't. That didn't work at all. What do we have here? Okay, so we've got the create true branch, create false branch split apart. So we're going to build a branch of the decision tree. We're going to find a feature which returns blah, blah, blah. But then we have this decision about gain of info. And this is our problem because I want to check for gain of info first. So maybe just the way I wrote the while loop was not good. So maybe what I should do is have like a conditional here. So this whole thing's a loop, have a conditional here. And if there's gain of info, then I say, okay, return leaf. And I can have a thing like, well, you don't like check in a recursive function and say, okay, we're all done, return everything. Every call of that function just returns itself. So eventually they're all going to return a leaf, and then this call for create true branch is going to return, and they're all just kind of like the whole stack is going to return. But let's just keep it a little bit at a time. Let's go to the conditional. Let's start with that. Okay. Let's even get rid of the loop. Like we don't need this. Forget about the repeat. And what does this look like? If, then, yes, no. Okay. So we can say if gain of info then yes or no, yes or else. Okay. Wow. If gain of info is yes, and then we're going to have this split thing. I need to like look into the Emacs code for indenting, because like for indenting plant UML, whatever the major mode is here, I'm not sure they understand. I mean, I'm okay if they want to use like a tab like that, but I guess it's fine. They know what they're doing, whatever. Okay. But I want it, but they don't. It's not nice like in Python or something. It's fine. Now we need the else. This is the thing. I'm like, they're not going to know. They want to indent that else, and it doesn't belong there, unless this belong. You know, else belongs back here, but they don't. They don't do it right. Okay, else no. See, stop it. I don't. We gotta fix this major mode. Come on, guys. If gain of info is no, then we're just going to have a thing that's like return leaf. There's more to it than that, but this is like the top level of this recursive function. Obviously, it involves like other function calls inside of it. And maybe we're going to end up getting all of that into one big complicated diagram. I'm not sure. Let's just see if this even works. What did I do here? I'm getting so stressed by like the indentations. Okay, else no. What's the problem with that? It's like exactly like n split should be like there. Why is n split have to get indented? Man, I'm gonna pause it. I'm not gonna do this on screen because I just want to like look up the plant UML major mode in Emacs and figure out how to fix it. So I'm not gonna waste people's time with that. Okay, we're just set plant UML to open up in text mode so that I don't have these crazy indenting problems. And so actually somebody did start indentation support. Sometime there 3 years ago there were some indentation improvements. And they gave a shout out to this one guy. Where did he go? Anyway, they gave a shout out to one guy in here for helping, Raymond. And I'm pretty sure Raymond did a great job. He did better than I would have done. But you know, it's not working for me at the moment. So until I can come back and fix this, text mode it is. Text mode is fine for plant UML. Who cares? We're not doing anything like super intense with plant UML. And it's a crazy... Like, it's not a super consistent language anyway. But now we have our if and our else and everything. And I think that it should work. Or do we still have errors? Error in line 18. Okay, else. So we did something wrong with this if, this conditional. We need an end if. That's good. I think this stop should go inside the end if, but I don't know if you can do that. All right, we got still a problem. This needs a semicolon. All right. Okay, now we have something kind of like what we're looking for. So we just need here, create true branch, false branch, actually needs to go back to build branch of decision tree. And then we're actually going to have to take a look at this code and figure out a little bit more what's going on. All right, so how are we going to do this while loop? Okay, so I got this while loop working, and I kind of, it clarifies for me how to think about this UML stuff. And this is great because this is why I was saying I was kind of cheating by just trying to go through the code and copy the code like into UML. That is the problem, right? I was like, well, you need to stop to understand that. And like, for instance, last time I was doing this, I stopped to understand some other thing. It doesn't matter now. Partition. So what we're doing now is we're saying there's a feature test with gain of info. I said probably I can say is there so it's easier. But is there a feature test with a gain of info? Yes. then here, create a true branch, create a false branch, build a branch of the decision tree. So we could simplify this even more. I could just say build a true branch, build false branch, and keep going, right? And then again, there's a feature test again, and that will just go forever. And we don't care if it's implemented recursively or with a loop or how you do it, right? That's not our concern here. And if no, then we need to return a leaf. And so the thing is, this is cool, but we're not sure that we've like really captured like this is not super clear, because like, how do I see that like all of my leaves turn into branches and so on? So I do need to read the code like a little more closely and understand exactly what's going on and figure out how to get that into this diagram. So that's what we're working on doing here. Read through the code. It's like we got a diagram. Now simplify the diagram some more so it reflects what's actually happening more. And then go through the code and be like, okay, like how do we make this more clear? And in particular, my question, I guess, is how do I make it clear, like at the end of all of this, all of these leaves need to turn into the branches and the branches need to turn into the tree. That's not, saying return leaf is just capturing what the recursive function does, but it's not capturing what the actual process is. So there's like the implementation. This is just an implementation detail. It doesn't really belong in the diagram at this level. So yeah, let's stop and think about that, see what we can figure out. I've clarified the branches, I've clarified the diagram a little bit. And in doing so, I think it's actually capturing the code better now. So we're saying, all right, the branch has a feature test. And feature test is what we're going to call this test. We could just, we should probably just call it a test, and then we have to define it somewhere else. So we say branch has a test. That's why he used the word question. We're going to use the word question too, because test is just such a commonly used thing. People might think we're talking about like unit testing or something. So we'll call it a question as well. It's probably a good choice that guy made. So branch has a question that produces get of info. No, add a leaf to the branch. That's what we got to do. Yes, then use the best test, the best question, to put training data into true and false partitions. Bam. Here we have a split, build branch with the true partition, build branch with the false partition. And then we go back. Branch has a feature test. Now, okay, so first of all, we need to define some terms, right? So the person reading this is going to have to at least understand what the feature... Actually, I don't know. This is probably okay. But I think there's still some details missing here about how do we build the branch. Well, we build a branch because... it's just like a question, like how do you represent data structures in UML? That's a good question. I don't know what that's about. We gotta look at that. But anyway, maybe we can make like a state diagram of not the code. Like the state diagram is not of the build tree function. The state diagram is of the tree. This is the state of the tree, or like a leaf. So then if we have like the state diagram and the activity diagram together, we could start to understand what the tree looks like. The way we build a branch is that we have a leaf, and it's just all the leaves come together. It's like, man, we all know what like trees look like. So you have like a node. I'm just moving my mouse around on the screen. That's not really good. But you have a node, and you have a node, and you have a node, and then they all go up to whatever their parent node is here. So what we actually get at each here, when we say build branch, we should really be saying like, a branch basically just means that one node now has two child nodes, and each of those child nodes is called a branch. And then at some point we get to where, hey, this child node doesn't have any children. Okay, it's not a branch, it's a leaf. And in doing this kind of recursively, that sort of gets built up. So this idea of having a branch is like kind of abstract. It's like I'm gonna have a branch when I found all of my child nodes and they found all their child nodes, and then we got finally to the point where a child node is a leaf. It doesn't have any child nodes. So yes, we have to really. I want to make this more clear exactly. Like, so this is like still not super clear, but we are definitely closer to what the thing is. But we're still relying on that recursive definition, which I don't think is good. Because that's really also an implementation detail. It's like, okay, so the best way sometimes to build up a tree is to use recursion. It's definitely the simplest code, but it's hard to understand. Like, I just had to like talk it through. It's certainly going to be hard to understand from this diagram. I don't know. It's you want both levels. I mean, the diagram should be able to say like, hey, we're building a tree. But I don't know. This isn't capturing it for me enough. This is not making it clear. Just saying build branch, it's like it's misdirecting you from the idea that actually what you're really doing is you're going to start building from this node, start building from that node. And if you say, hey, there is no feature test, you just say, okay, this node doesn't have any. And so you don't have to do this. You could do this in like you could do this with some like normal kind of iteration. You wouldn't have to use recursion necessarily. So we're going to look at how to represent this better, and also we need to find out what does it mean to represent a data structure in UML? And that would be important because the decision tree, literally, it's a data structure. Like, we are building a tree. So this is pretty critical to what we're doing here. Okay, this is putting me on the right track here. I just randomly found this lecture slides just searching for UML data structures. And basically here they're saying, okay, the tree, let's say we have a class that is a tree, and then it's going to have these methods like, create node or create branch or whatever. If we actually start with that, so if in this activity diagram, I had the concept of a tree object, that would make this whole thing much easier. Because then I could actually go into my tree object, and maybe in here, in the tree object, okay, here they show an implementation of it, whatever this thing does. But maybe I can actually now create a diagram to give you the implementation of the tree object. And and this is kind of what this does, but this is also including this idea of the feature test. So, okay, that's cool. I have this idea of the feature test. If, we have to keep adding branches to the tree until we find no more gain of information. So this is mixing two ideas. It's mixing like this process and also the object of the tree. So if I've been thinking of the tree as an object the whole time, it would then have its methods. So I'm going to end this video here because I think half hour is about long enough for anybody to struggle with UML and stuff. Like, this is a pretty boring video. But I think I'm going to do the next video, which I'm going to start in a few minutes after I take a quick break. I think is going to be better because I'm going to try to basically take something like this and describe an implementation of the tree. And this also gets into maybe part of the idea of UML of like maybe implementation details can be left out of it. Like maybe I don't need that. But what I'll try to do possibly is find a simple tree implementation. Like, we don't need like a balanced tree or, I already have like this decision tree implementation, but in this code, here we go. So we have a leaf and a decision node. So we have basically our thing. So I said in the first video that if I started at a lower level, it would have been easier. That is true. I need to have a tree object first before I can do this building of the tree. So I'm saying, yeah, let's build a tree, but I missed some like key abstractions that I needed to have in this loop. So I'm going to start with actually trying to describe my tree object, and if possible, even like I want to describe the implementation of how it works. So we are still trying to read this code one-to-one basically and capture this particular implementation of a decision tree in UML. And we're just deciding now, we're learning now. Like even here, I could have got this clue. It says return decision node, right? That's here's return leaf, here's return decision node. I should have captured these right in the beginning, and all of this would have been much, much simpler. Now I still, here's the thing though, like if I just copy it one-to-one, there's still this idea of the recursive thing. So, all right, I don't know what I'm doing, but this is what we're headed for next. We're going to just work on how can we describe a more low-level implementation of something. I don't know if any of it makes sense, but I'm just gonna do stuff, and we're gonna see how it turns out.